We call something that looks like this a quadratic expression. A quadratic is a polynomial with a degree of 2. A polynomial is something that looks like this. It has one variable multiplied by its coefficients, and that variable is raised to a non-negative power. If the highest power of the variable is 2, that makes it a quadratic. If we set our quadratic equal to y and plug in various values for x and calculate the corresponding y values, when we graph these x's and y's, we'll get a curve that may look something like this. We'll get something like this when a is positive, the coefficient of x squared. If a is negative, our curve is going to open downward. We call these shapes parabolas. So technically, a parabola is not the same thing as a quadratic, although when you graph a quadratic equation in terms of y, you will generate a curve that we call a parabola. But colloquially, these terms are often used interchangeably, and it's not worth getting too hung up over it. Now I'm going to prove that the locus of points represented by a point P that are equally distant from a point and a line that doesn't pass through the point, this locus forms a shape that is a parabola. Since the parabola is the graph of a quadratic expression, it suffices to show that these points satisfy an equation that looks like this. When we expand this squared binomial, our highest power of x is going to be x squared, so this is a quadratic. We're going to call this point the focus of the parabola, and we'll label it f. I'm going to say that the x-coordinate of this point is h, and the y-coordinate is k plus p. K plus p seems like an unusual choice to label our y-coordinate, but it will make sense later in the proof. The line is called the directrix, which I'll label capital D. For this proof, we're going to make it a horizontal line, and its equation is going to be y equals k minus p. Again, k minus p seems unusual, but it's chosen for convenience, and you'll soon see why. We can do a similar proof for a vertical directrix, but a diagonal directrix, that proof is very hard. So we'll continue on with the horizontal directrix. Let's make this pink line be our directrix, y equals k minus p. And let's say this is the focus, and we're going to try to find points that are equally distant from this point and this pink line. First, we'll find an easy one. Let's draw a perpendicular from the focus to the directrix. We'll call this point Q. Its x-coordinate is the same as that of the focus, that's h. Its y-coordinate is the same as the directrix, that's k minus p. One point that's equally distant from the focus and the directrix is this point V. V is the midpoint of segment FQ. Since VF equals VQ, then V is in our locus. Its x-coordinate is h, the same as that of F and Q, and its y-coordinate is directly between k plus p and k minus p, so its y-coordinate is k. And this is why I chose k plus p and k minus p for the y-coordinates of f and the equation for our directrix. Now we're going to find an expression for all the other points p that are equally distant from the focus and the directrix. That means the distance from p to f is going to be the same as the distance from p to this point r, where pr is perpendicular to the directrix. If pf equals pr, then we can square both sides of the equation. Drawing this perpendicular from F to PR, we'll call this intersecting point S. We can use the Pythagorean theorem on this triangle or the distance formula to find the square of the distance from P to F. This distance from P to S is the distance from P to R minus the distance from S to R. The distance from P to R is just the y-coordinate here. The distance from S to R is the same as the y-coordinate of the focus. That's k plus p. This distance from F to S is just the difference in the x-coordinates of this point S and this point F. That's x minus h. So we'll plug these in to our expression down here. This is the square of y minus k plus p plus the square of x minus h. Now we'll find pr squared. Pr is this vertical distance from p to the directrix. That's the difference in the y-coordinates between this point and this line, or y minus k minus p. So we'll take the square of that, and that's pr squared. Again, every point in our locus is the same distance from the focus as it is to the line, which means we draw a perpendicular from the point to that line and find that distance. If pf equals pr, then the squares are equal to each other. So now we'll set these two expressions equal to each other. By substituting, we'll expand both of these first, combine like terms, and expand some more. We find more terms to combine, and I'll collect all the y terms on one side and everything else on the left-hand side. We'll switch both sides and divide by 4p to solve for y. P is just a number that depends on the distance between the focus and the directrix, so we can let a be 1 over 4p, and our equation becomes more familiar. Again, it's a quadratic because when you square this binomial, our highest degree will be 2 because of the x squared term. And when you plug in various values for x, you will get a curve is in the shape of a parabola. For example, take our vertex, which was hk. If we substitute x equals h into our equation, this part becomes 0, and y is equal to k as expected. This works for any focus or directrix that's horizontal that you can think of. So for example, you can choose a focus with an x-coordinate of the square root of 3 and a y-coordinate of 2 million, and a directrix with the equation y equals negative 7 pi. Let k plus p be the y-coordinate and k minus p correspond to the equation for the directrix. We'll add these equations together and we can solve for k and p. With h given as the square root of 3, we can plug this into our parabola equation, and all the points that are equally distant from this point in this horizontal line, those points have an x and y coordinate that satisfies this equation, which also graphs as a parabola. If you'd like me to solve any other math problems, please leave them in the comments.